Hello everyone. In the previous video, I have shown you how to derive differentiation formula. But in that video, I have shown you how to do it in a reverse engineering method. And now I'm going to show you a different way, which is a forward engineering method. But it will use what we call as binomial expansion. And it's a little bit large, a very big scope to be covered in this video. So I will give you a very brief primer regarding binomial expansion. So shall we? So let's begin with the equation y equal to ax to the nth power. Alright, and I'm going to prove it to you that the differentiation for that dy over dx is equal to a multiply n x to the n minus 1 power. Okay, we begin with y equal to ax to the nth power, and I call this as equation 1. And if we can visualize the curve of y, it probably looks like this, and that's the point what we call x here, and point y, corresponding value of y for any given value of x. So if we increase x by delta x, a small increase, so this point is now x plus delta x. And if there is an increase of delta x, there will be an increase, corresponding increase by delta y. So this value is now y plus delta y. Okay, so we will develop a new equation, which is y plus delta y equal to a. So x is now x plus delta x to the nth power, and I call this as equation 2. So now we are going to perform binomial expansion of x plus delta x to the nth power, and I'm going to show you step by step the easy way by, say, I'm going to choose a different color here now, x plus y to the nth. Yeah, I'm going to just borrow variable x and y for a while for any given integer value of n. So if n is equal to 0, then what we will get is x plus y to the power of 0, which is obviously equal to 1, because any real number that is powered by 0 will equal 1. So if n is equal to 1, then x plus y to the power of 1, that will equal to x plus y. So this is really straightforward. So now comes the hard part. N equal to 2. If you're already familiar with binomial expansion, then this is, well, not a problem for you at all. So x, if n equal to 2, then x plus y to the power of 2, that is equal to x plus y multiplied by itself, multiply with x plus y. And we're going to multiply each component in this first bracket with each component of the second bracket. So I can also write it as, I'm taking the first x here and then multiply with x plus y, the second term in this bracket, plus y, which is the second component here, multiply that with x plus y. And now I open the bracket to multiply them all. So x times x is x squared plus xy, and over here y times x is yx, or I can just write it as xy as well to make it consistent, and y times y, that equals y squared. So now we are going to add up all the like term, which is xy and xy. So we're going to have x squared plus 2xy plus y squared. Okay, that is quite simple, and things are going to get a little bit more tedious if n is equal to 3. Then that is x plus y multiply with itself 3 times. Or I can write it as x plus y squared times x plus y. So I'm going to take the expression here to multiply that with x plus y. Give myself some real space here. So now x plus y squared is x squared plus 2xy plus y squared. Multiply that by x plus y. Or I can write it as each component of this first bracket multiply with x plus y. So first one is x squared plus times x plus y plus 2xy times x plus y plus y squared times x plus y. So now we get x squared plus x is x cubed plus x squared y. And the second one, 2xy times x, that is 2x squared y. Okay, and then 2xy times y, we have 2xy squared. And the last expression, that y squared with x, so we have x y squared plus y squared with y, then y cubed. So we're going to add up all the like terms, which is x squared y, is x squared y here. Oh yeah, first is x cubed plus x squared y plus 2x squared y, that is 3x squared y. And the next one, the next like terms is xy squared, so that becomes 3xy squared, and the last is y cubed. So I wanted you to take a look at a few characteristics here. First, I arrange in such a way that I have a decreasing value of power of x, okay, x cubed, x squared, x, and with x nothing, and increasing value of y power, which is from y nothing to y to the power of 1, y to the power of 2, to y to the power cube. And then the most important thing that I want to show you here is the coefficient, this coefficient, and from this example, this coefficient. Well, there are some hidden coefficient which is here, and the value is 1. Likewise here, let me just erase the bracket. There's coefficient of 1 there. I'm going to rewrite that as 1 with the coefficient, the hidden coefficient, x cubed, and I'm also including the y here, but with the power of 0. As you know, any real number, when you power that with 0, that becomes 1. So there is no effect whatsoever by this coefficient and this y to the 0 power here. I'm putting it there so that I can show you what I want to, what the points I want to raise here. And the coefficient, the second coefficient, 3 x squared, okay, decreasing value of x power, now with increasing value of y power, y to the power of 1. And the third coefficient, 3, decreasing value of x power, which is x to the power 1, with y squared this time. And the last coefficient, 1, with x to the power 0, that is the hidden x term, with y cubed. Alright, now let's put the coefficient in bracket. Now let's take a look at this. The first coefficient, well, that is kind of looks ugly. Let me just do that. Redo this like this. Okay, now take a look at we have n equal to 0, n equal to 1, n equal to 2, and the third example, n equal to 2. The coefficient of the first coefficient is always 1, the second is 2, and the third is 1. In the fourth example, I have the first coefficient is 1, the second coefficient 3, the third is 3, and the last is 1. As you can see, the first coefficient is always 1 in both third example and fourth example, and the second coefficient is 2. And that is the same as the value of n, the power of the binomial. Likewise, on the fourth example, the coefficient 3 is equal to the power of the binomial. I want to put that as in the different representation. The coefficient, I'm going to put that in with variable c. Okay, c for coefficient, and I will put 3 here and 0. That's the reason why I do that. I will explain it. I'll explain that later. And then x to the power of 3, and I'm gonna put that as 3 minus 0. The next term is y to the power of 0 plus the second coefficient. We shall name it as 3c1 with x 3 minus 1 and y to the power of 1. And the third coefficient, as you can see the pattern, is 3c2 x to the power of 3 minus 2 and y to the power of 2. And the last one is 3c3 x to the power of 3 minus 3 times y to the power of 3. Reason being is that I want to show you as it goes up from 0 to 1 to 2 to 3, there will be corresponding changes to the value of this. Take a look at that, yeah? Alright. And this corresponding the same value here and here, 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 and here. Alright, now I hope you follow me so far. If you don't, please repeat this video. And I'm going back to the original expression, giving myself some space, which is x plus delta x to the power of n. And I'm going to put that in the general expression as n c0, following the same standard as I did here, and x times x to the power of n minus 0, and then y, well, not y now, then delta x to the power of 0 plus n c1 x n minus 1 times delta x to the power of 1. And then moving on, n c2 times x n to the power of 2 and delta x to the power of 2. So now we do not know what value n is, so it just goes on and on and on, endless. That's why binomial expansion is a bit tedious and very, very lengthy. I'm gonna put just the last 3 terms here, and I'm gonna do that below. Alright, and c n minus 2, multiply that with x, and minus what? Okay, n minus must be the same value of this one, which is n minus 2. So n minus 2, what is that? Well, that is the same as 2. Okay, n minus 2, that is equal to 2. So I'm gonna delete them. I'm gonna put that as 2. And delta y now to the power of n minus 2, and the second last term, which is n c n minus 1, so x to the power of n minus 1, that is basically equal to 1. And delta y, that is power of n minus 1. and the last term, which is ncn x to the power n minus n, which is 0, multiply with delta y to the power of n. Okay. And this lengthy, very long expression can be represented by the symbol of summation. I hope you're familiar with this symbol. If you are not, then probably it's a good time for you to do some Googling. I'm going to introduce a new variable, which is r, starting from 0, within CR. X to the power of n minus r and y to the power of r. Okay, let me tell you a little bit about this representation here, NCR. This is basically a combination formula. We can also write them as NR, like this in a bracket vertically, or the way we say it in mathematical term is n choose r. N choose r. So I can also rewrite that summation like this. From r equal to 0 to r equal to n choose r times x to the power of n minus r y to the power of r. And for those who are interested in this combination formula, that is actually equal to n factorial divided by r factorial n minus r factorial. You might want to Google the topic of combination to understand what that is. Okay, as I have already highlighted to you that the first coefficient is always 1. The first coefficient is always 1. The second coefficient is always the same as the value of n. The second last coefficient is also equal to n, and the last one is always 1. So I can write that, I can summarize that as, I'm going to write it here, NC0 is always 1. And NC1 is always equal to n. If you don't believe me, you can use your calculator. I have my own calculator here. Take a look at this. NCR, n choose r is here. I'm circling it here with my my mouse here. Okay, let me choose. Let's say n equal to 5. No, let me choose n equal to 2. Okay, the same example as this one. Okay, I'm gonna prove to you that the first coefficient is 1, the second is 2, and the third is 1, and then I'm gonna choose the value of n equal to 3. So what is the value of 2C1? Gonna use my calculator again. 2, and I'm gonna press shift so that I can select the NCR value formula, and 0, that is equal to 1. Okay, that's the first one. Oh yeah, I got this one wrong. It's supposed to be NC0, so that is equal to 1. So what is 2C1? Well, not n. 2C1, what's the value? 2C1, that is equal to 2. So now it's proven. I'm not going to do the third coefficient because what matters to me is the first and second. So let's pick another example. Let n equal to 3. Okay, so what is the value of 3C0? 3C0 is equal to 1 again. And what is the value of 3C1? C1 is equal to 3. Alright, for the sake of proving it, let's find out the value of 3C2. It must be equal to 3 as well. Okay, and 3C3 must be equal to 1. Okay, there you go. Alright, now let's continue. Okay, I'm gonna put that expression back into equation 2. This equation. Alright. So y plus delta y, that is equal to a. Okay, remember that's still our multiplier a. Yeah, let me just write back what I had before, which is y plus delta y equal to a x plus delta x to the nth power. Alright, I'm gonna replace x plus delta x to the nth power with the expression in the square bracket. I'm gonna put that as n choose 0, x to the power of n, delta x to the power of 0, plus n choose 1, x to the power of n minus 1, delta x to the power of 1, plus n choose 2, x to the power of n minus 2, and delta x to the power of 2, and plus the rest. I'm not gonna be bothered to write them all. And now I'm gonna open up the square bracket so we multiply with a. Alright, so now n choose 0 is 1, so I'm gonna leave that behind. So now become a with nothing, with 1, x to the power of n. So what is delta x to the power of 0? That is equal to 1, so I'm not gonna write it down. Plus the second term, the second coefficient n choose 1, that is equal to n, okay, as proven before, x to the power n minus 1, and then the delta x power of 1. Next term is n choose 2. I'm not going to be bothered writing the value. I'm just writing down the general representation, x to the power n minus 2 and delta x. Oh, I forgot a here. Delta x squared plus everything else. Okay, this is y minus delta y. And I'm going to name this as equation 3. We have equation 2 here. By the way, the original equation y is equal to ax to the power of n, which we named that as equation 1 before. I'm going to put it back here. And we are going to manipulate equation 3 and 2. Equation 3 and 1 by subtracting equation 1 from 3. So what do we have when 3 minus 1? Okay, take a look at the left hand side. Now this is y minus delta y, yeah? Not y plus delta y, not y minus delta y. So on the left hand side, y plus delta y minus y, what will we get? Yes, y plus delta y minus y, then we're left with delta y. On the right hand side, we have like terms. Ax to the nth power, same. So when we minus this with this, then we will left with nothing. So we will have the rest of the expression only. Okay, now we have a n x to the power of n minus 1 delta x plus a n choose 2 x to the power of n minus 2 and delta x squared and plus the rest, which I'm not gonna be bothered writing them down, and I'll show you why when we apply limit later on. Okay, now everything, all of this expression, I'm gonna divide them by delta x. So on the left hand side, then we have delta y over delta x equal to, alright, the second expression, we have en x to the n minus 1 and delta x here. So when delta x divided by delta x, that will become 1. So I'm going to have only a n x to the n minus 1. Delta x is gone. Okay? And the second term is a n choose 2 x n minus 2. Alright, delta x squared divided by delta x will have only delta x to the power of 1. Okay? And everything else follows. Okay? Now, let's apply the limit. So if I have limit as delta x approaching 0, we are coming to the end, that is equal to the limit as delta x approaching 0, a n x to the n minus 1 plus limit as delta x approaching 0 of a n choose 2 x to the n minus 2 delta x plus everything else. Okay, on the left hand side, when limit delta x approaching 0 of delta y over delta x, that becomes the differentiation expression, which is dy dx. Okay, on the right hand side, the first term, as delta x approaching 0 to the expression of en x to the power of n minus 1, that will not change anything because there is no delta x anywhere in the first term. So we have only an x and minus 1. What about the second expression? As delta x approaching 0, we have delta x here. So delta x is now extremely small number. When it's multiplied with another expression or another number that is a real number, that has become, the product has become insignificant. So this basically disappears. And the same as all the other expression, you can imagine that there is a delta x squared here, well, with all the multipliers plus everything else, delta x cubed and the rest, everything disappear as delta x approaching 0. Well, they just do not disappear, they just become too insignificant. So in the end, we will arrive to this delta, well, not delta, dy over dx is equal to an x n minus 1. And that is how we prove the formula for differentiation. Dy dx equal to an x to the power of n minus 1. And everything is now proven. I hope you learned something from this video. And of course, it's a little bit lengthy. The video is long. So if you have any difficulty, please just repeat this video. And I'm also going to attach a text, just like the one I wrote here, so that you can make that as a reference. So I wish you success, and please continue with the remaining videos in this lesson, and I wish you all the best.